So we are going to start with a new chapter today, which is called as magnetism and matter. Let us discuss what exactly is magnetism and matter. First of all, let's see the history from where it all began. So it all, there was a substance which is called as, which was named as lodestones. And these substances, they were rock-like structures, and they had ability to attract small pieces of metals over a short distance. Earlier I thought that I'll be giving, acha, by the way, I'll be giving you some notes because this is more of a theoretical based chapter, so I'll be giving you some notes as well, apart from the notes which I'll be giving you over here. Okay, I told you about this already, right?
Yes, sir.
These lodestones, they are generally used in used to make compasses, the magnetic compasses or magnetic needles which I have now, and sometimes they are used in electric motors and generators as well. Okay, also around 600 BC, there were these Greek people. Due to certain phenomena, this place, or basically this island, or whatever it is, where they first observed this, was basically in the town of Magnesia. Magnesia is the name of a town where all this began, and from this town, the ore which on which they were walking, the ore, or basically the whatever the soil or the area or whatever it is, it was named as magnetite. Sounds like the name of a Pokemon, but it is not. And this phenomena is termed as magnetism. Is this clear, guys? And later on, this magnetism was developed by many scientists. People started researching on it. And what do we know now? We know now that magnetic field, the magnetic field, or basically the magnetism, is observed in various things, right? They were observed in bar magnets and all, right? They were observed when this phenomena was observed when there were moving charges. When charges were moving, then also it was creating certain magnetism. We already learnt in chapter 3. And by the way, you will be having a test on chapter 3 as well. I've already updated somewhere. But I wanted to ask you people, do you want me to take a test completely on electrostatics till current electricity as of now? Because me and Kunal sir were discussing regarding the same. Whether we shall conduct a part test or whether we shall conduct a chapter test. So chapter test is a must. So we'll conduct the chapter test, but we'll be conducting this part test as well. So before and after, that was the topic कि पहले part test ले, बाद में chapter test ले, कि chapter test लेके फिर part test ले. So it is still in process. So whenever any update will come, I'll give it to you, and you'll be informed in the groups as well. है ना? Whenever there are current carrying conductors, then also this magnetism was observed, right? So you all know about all these particular things. Now, uh, I have done written writing till here. Please remember, it's a theoretical chapter, so nothing much to explain over here. It's just like a story which as I'm telling you. There was one theory which is called as the molecular theory of magnetism. According to this theory, every molecule of a substance is a complete magnet itself, and this magnetism which is developed in the molecule, it is assumed to be, or it is believed to be, made of smaller smaller molecular magnets inside the molecule, right? Yes or no? If these small molecular magnets, why am I making you write all this? Because so that at least if someone asks you about a little bit about the molecular theory of magnetism, then you can write at least some points, है ना? If this molecular magnet are randomly oriented, if they are randomly oriented, then we can consider, you remember, if there is any metal, we call it as grains. There are small grains inside metal, we assume them as grains, and each grain has its own molecular dipole moment. Then we can consider the overall or total magnetic moment as zero. We'll study about more when I'll be discussing the characteristic. Well, I'll be discussing all the properties, magnetization, susceptibility, and also we'll be coming back to this molecular magnet theory again. And hence it is not magnetized. Okay, if they are all oriented in one particular direction, then to give a net magnetic moment, then we say that material is magnetized, and hence will possess the property of magnetism. Okay, so suppose if I have a material in the shape of a bar. So in one case, can you see? I can have these small materials. We'll come back. I told we'll be coming back to this property again. So don't worry, we will not come back. So there are small material. These. There are these grains inside. Let me just copy and paste them again. Draw this up. So in this case, can you see there are small grains of molecules, right? So if I say inside these grains there are these small molecular magnets, and let's say the dipole moment of this is in this direction. Let me change the color. Let's say the dipole moment of this is in this direction. Let's say the dipole moment is this. Let's say the dipole moment is this. Let's say the dipole moment is this. Can you see over here? The dipole moment is randomly oriented in all possible directions. Whenever it is randomly oriented in all possible directions, then what will happen? The net magnetic moment will be, guys, the net magnetic moment will, when it is randomly oriented, then net dipole moment is
0.
0. Or net, which dipole moment am I talking about? Net, in spite of using dipole moment, you use magnetic moment over here. The net magnetic moment is 0. These materials are basically your unmagnetized okay. And similarly, if I draw these as magnetized, then what will be the case of how do you magnetize and unmagnetize substance and all? We'll discuss all of them later on in the chapter, later on, way later on. Okay, so can you see the dipole moments of every grain is now arranged in the same direction? The net dipole moment. So all these molecular magnets, all of their dipole moments are arranged in the same direction, and hence the overall substance, it produces certain magnetic moment. Okay, so these substances are basically your magnetized substance. Please remember, whenever I say any dipole moment like this, then if I draw like in terms of magnets, then this will be south, or shall I thoda sa zoom more? This will be south, this will be north. This will be south, this will be north. This will be south, this will be north, this will be south, this will be north. Are you getting my point, guys? So if the molecular magnets are arranged like this, then this will be the case. Can you see? Then only their magnetic moments will be in this direction. Is this clear? And here in this case, what will happen? Some molecular magnets will be like this, south over here, north over here, and this magnetic moment of this one may cancel out with some other one. Since it is randomly oriented, so can you see it will get cancelled out? Some may be arranged like this. If you see it in vector form, automatically you will see that the magnetic moments are cancelling out. Sorry. can you see the magnetic moment of this is in this direction and the magnetic moment of this is in this direction, equal and opposite, cancelled out. The magnetic moment of this is in this direction, the magnetic moment is in this direction, the magnetic moment is in this direction, the magnetic moment is this direction. Can you see? It makes a closed loop. And what is the resultant of equal vectors in a closed loop? Not necessarily equal. If the all of them can be arranged in such that the loop is completed. So can you see overall of this 4 will be also 0? Are you getting my point? Yes or no, guys?
Yes, sir.
So these are your unmagnetized substance and these are your magnetized substance. I hope you have written till here and it is clear.
So moment is always from south to north?
Yes, it is. In the case of bar magnet, it is always from south to north. And I'll tell you the reason also. I'll make it analogous to your electricity dipole. Okay? Electric dipole. Whenever you're done, just tell me. We'll discuss more about this property later on. Don't worry. Or if I will be having some points missed, then I'll give you some notes. Usme wo points there will be those points mentioned clear. I'll share it to you. Because it's like I don't have one material which is at only one particular place. I have different material, but some notes will cover something else, some notes will cover something else. So that's why I try to give these notes so that it will be combined everything at one place. I try my best to do that, but sometimes even I miss points. And I told you this is the first time I'm teaching this chapter, so I may miss some points. That's why I'm giving you the notes so that in case if some point is missing, then you can check in that. Okay. Chali. Yeah, we're done noting now.
Yes, sir.
Let's learn about the bar magnet. Now, what is a bar magnet basically? It is an arrangement in which two equal and opposite natured magnetic poles are separated by a very small fixed distance. So please remember, even if the poles are separated, they are not allowed to touch each other. They will be separated at a small distance, or you can, in spite of writing this, by a very small distances held fixed with respect to each other. So can you see the definition seems to be similar? What was the definition? Is this definition somewhat similar in electrostatics? We used it somewhere. Can you see? Do you remember the electric dipole?
Yes, sir.
Electric dipole was basically when
Yeah.
two equal and opposite charges were separated by a very small distance and held fixed to with respect to each other, right? That was called as an
Yes.
electric dipole. So basically, this bar magnet is also called as a magnetic dipole. That's why this bar magnet is also called as a magnetic dipole. Is this clear? What are these poles? Guys, what are these poles? In the case of a bar magnet, or whenever you give any dipole moment, mention it with the help of using this term poles. What are these poles? Can anyone tell me what are these poles? They are the points on the magnet. Since we're defining the poles of a magnet, they are the points on the magnet where the magnetic field intensity. Achha, magnetic field intensity has another name, right? Where the magnetic field intensity or magnetic induction is maximum. Yes or no? So basically, we assume them. We call poles as basically those points where the magnetic field intensity is maximum. Is it clear? How many poles we have defined?
2.
There are two poles defined, the north pole and the second one is the south pole. North pole is basically that pole from where the magnetic field lines are coming out, and south pole is basically that pole where the magnetic field lines due to the magnet are going into the magnet, coming out of the magnet. Is this clear, guys? North and south? Is this clear?
Yes, sir.
So when we draw it like draw the magnetic field lines very carefully. Instead of copying one by one, I can copy the whole thing, right? Now I can copy. ऐसे स्मार्ट में बचपन से था क्या? बट आई नेवर घमंड कभी नहीं किया मैंने एवर. So suppose if this is the north pole, this is the south pole, then the magnetic field lines will be appear to coming, appear to come out of this particular north pole, and they will appear to enter through the south pole of the map. So I guess it is clear. Is this clear?
Yes, sir.
And please remember, the outside the magnet, where does the field move from? Outside the magnet, it moves from north to
Not south.
south. Outside the magnet, the field lines move from north to south. But what about inside the magnet?
South to north.
South to north. We assume it to be moving from south to north. Why? Because the magnetic field lines are always in the form of closed and continuous
Close.
loops. I have already discussed the properties of magnetic field lines. How do we determine where the poles are? The poles are determined using the iron filling experiment, right?
Yes, sir.
Acha, there is one property of bar magnet कि whenever a bar magnet is suspended freely on Earth's surface, then where in what direction will this magnetic, will this bar magnet align itself? Freely from a thread on Earth's surface, then the magnet please remember it approximately points towards the geographical, not actually points towards. Why does this happen? We'll discuss it later when we'll discuss terrestrial magnetism, Earth's magnetic field basically. In the geographical, then the magnet's north pole point towards the geographical north approximately. Clear? Or we can say the magnet lines itself approximate north south direction. Yes or no? Please write this point. And why did I say use the term approximately? It's because there are two different poles in the case of Earth. You'll learn it later when we'll start with terrestrial magnetism. That Earth has geographical north as well as something called as magnetic north. Magnetic north is different, geographical north is different. I don't know the reason. Even nobody knows the reason why it is different. It's how Earth was made. So during the formation of Earth, maybe something might have happened which might have caused this. I don't know. So, anyways, right till here. We know this particular thing, a current carrying solenoid whenever we're done till here, tell me we'll continue. Chali done.
Yes, sir.
Acha, always remember the poles of a bar magnet are not exactly at the ends of the magnet. They are at some distance inside. Okay, so if someone tells you that this is your bar magnet, and let me just, why am I taking this? If someone says that this is your bar magnet, and exactly at this particular point and exactly at this particular point, let's say this is your north and this is your south, so ऐसा नहीं होता, this is wrong. Okay, what actually happens that the north pole and the south pole, they are little bit inside the magnet. So if I say the length of the magnet is how much, if I say the length of the magnet is L, this L is basically what, let's say LG. LG is basically the geometric length of this magnet. But actually the poles are not separate. Please remember, whenever we talk about any length of the magnet is basically the distance between the poles of the magnet, right? So actually this length is the effective length, and it's the effective length of the magnet. Please remember this thing. Okay, whenever we talk about the length of the magnet, it's basically the distance between the north and the south pole. And always remember, this effective length will always be less than the geometrical length, as poles lie a bit inside the magnets near its clear. Shall we write about the next point?
So why does this happen exactly?
Because when you see this diagram, you see like the lines are emerging from this north pole, but actually it doesn't happen flow. Lines they're never tangent to on this particular surface. They come from appearing to be come from this particular point where the field is maximum. ऐसा होता है.
Mm.
So when you produce the line further inwards, it looks like कि all the lines are much more concentrated at this point rather than being concentrated at this point. अब तो you to know my diagrams are like this. When you will see it in a perfect diagram, you will see over here. Or shall I download the perfect diagram from internet?
No, sir, I mean it's understood.
है ना? तो ये यहाँ पे it will feel like they are a little bit separated away, but at a point inside, they are more closer as compared to the outside. So it was observed that the poles are not exactly at the ends; it was at a certain distance inside.
Okay, sir, got it.
And I think maximum this lecture, this chapter will take only 3 or 4 lectures. उससे ज़्यादा time we will not spare for this. We'll start with alternating current after this, and once we're done with alternating current, then we'll do electromagnetic waves. Okay.
Okay, sir.
Sure. Next point is, I just suppose if I have a magnet, suppose guys, if I have a magnet and if I break this magnet into 2 pieces, if I break this magnet into 2 pieces, then what will happen? Will it be the case if I break it from here, suppose? So will it happen like if the north pole is like this, the north pole will remain over here only and south pole will remain over here only? Can I separate these poles from each other?
No, sir.
Never. So basically what will happen if I break this magnet like this?
Each piece will have its own north and south.
So basically this north will induce an equal and opposite
South.
south over here, and this south will induce an equal and opposite
North.
north over here. So basically when you will break the magnet like this, it will become 2 smaller magnets with increased pole, a little bit decreased pole dipole moment, because the distance has been now decreased, right? We'll see the dipole moment and all, so don't worry. So is this clear? Similarly, suppose if I have the same magnet, control C, control V. In spite of breaking it from the middle, if I break it from here, now tell me what will happen. If I break it like this, then what will happen, guys? Will it become like this? Yes or no?
Yeah.
We'll see about how when breaking the magnets like this, wait a second. How is the magnetic field, or there are some factors which are affected when I do this, you know? So how do all those factors they get affected? We'll come back to this thing again, you know? Why is this happening? Note, whenever a magnet is broken into pieces, then in those small pieces, always a pair of north south will get formed or induced, whatever you want to write, making every one of them as a small bar magnet. Is this clear? And why does this happen? Why? Because monopoles never exist in the case of magnetism. In case of magnetism, monopoles will never be there. Acha, I have a trick question for you. Suppose you have a current carrying conductor. You remember no? Whenever current is flowing through this particular thing, a current carrying wire, poles will be induced, right? Yes or no?
Yes, sir.
Do you remember the clock rule I said? Whenever
Yeah.
the current is anti-clockwise, oh sorry, whenever the current will be anti-clockwise, the north pole will be there, and whenever it will be clockwise, the south pole will be there, right? So now my question
Yes,
is,
sir.
a current I is flowing inside this current carrying coil. Which pole will be induced over here? The answer is north pole or south pole or both pole or basically none of the above. Tell me which pole will be induced in this case. Current is
Both.
clockwise. Current is clockwise.
Both poles.
Current is clockwise.
But monopoles don't exist.
Exactly. Still both poles will be existing. And in this case also both poles will be there, but the pole which you will be facing
Yeah.
is given by basically this clock rule.
Mm.
Are you getting my point?
Yes, sir.
Please remember, clock rule gives the pole which we are facing. So which pole will be seen over here? The pole which you will be looking at will be the south pole, but automatically when you look from the backside of this coil, there will be a north pole as well. So whenever remember this, I gave this question to 12th grade, everyone did it wrong. I told them the fact whether this is wrong. Monopoles doesn't exist, but still they did it. So anyways, I hope this question 12th grade people at least they don't do it wrong, enough. So whenever current is flowing through the magnet, both poles will be created. You will be seeing only the south pole. That's the difference, right? Enough.
Yes, sir.
Yes,
So
sir.
remember this thing. Anyways, so this is all about your bar magnet and all. Let's discuss some more terms. Please write a heading. Pole strength. Denoted by M, small m. What is pole strength? It is basically defined as the name suggests, the strength of the magnetic pole to attract magnetic materials. Okay, basically you can say it is a measure of the magnetic field produced by a magnetic pole. Okay, please remember this pole strength it is analogous to electric charge in electrostatics. Do you remember electrostatics? How the electric charge Q behaved in electrostatics, this pole strength small m behaves exactly same in magnetism. Is this clear, guys?
Yes, sir.
Please write down the SI unit of this is ampere meter. Please imply ampere multiplied by meter, okay? Not ampere per meter or anything, ampere meter. Dimensional formula, I think you can calculate. I can give it as a homework. Or no need to do homework. क्या है? अभी कर देते हैं. The current is I or A, whatever you want to write, and the length is L. So M0, L1, A, T0, A1. Anyways, full strength clear है? Same. We'll see how exactly same it behaves. Okay. This pole strength will decide कि how strong a pole of a magnet is. Not necessary. हाँ, मतलब how strong a pole is. Whether it be a magnet or whether it be a current carrying conductor, or if you are introducing certain poles, then we'll see. Okay. Shall I move forward? Yeah, give me 2 minutes. I'll be just back. Done, guys. And here is the next heading. I hope you still remember this guy. You remember that?
Yes,
Yes,
sir.
sir.
This guy gave Coulomb's law for magnetic forces as well. He gave this law. He gave one law in electrostatics, one law in magnetism. So basically, what is this law? You can say this law gives the interaction force between two isolated monopoles or not necessarily monopoles, two isolated magnetic poles. For example, if uh, there are two magnetic poles Arey, I forgot to mention you this thing. How positive charges behaved in the case of electricity. Please remember the positive charges in electrostatics, they are same as how the north pole will behave in a magnetic field. Positive charges in electric field will behave exactly same as how a north pole, a unit or basically a a monopole north behaves in a magnetic field. Similarly, if I have a negative charges over here, I forgot to tell you this first. It behaves exactly same as how a south pole doesn't. So remember this point as well, na? Positive charge analogous to north pole and negative charge is analogous to south pole. So suppose you have two magnetic poles of pole strength M1 and M2, and let's say I have separated them by a distance R. So separated by a distance R, then I can draw this. Suppose this is your having M1, this is your having M2. Let's say this is also north and let's say this is also north. So between these two poles, what will be the force? Will there be a force of attraction or will there be a force of repulsion?
Repulsion.
The repulsive force will be F and that force will be equal and opposite, right? So this force F, the magnitude of this force, shall I write it like this? So F12 is equals to F21 and this is equals to F. So the magnitude of force is directly proportional to the product of the pole strengths and the magnitude of force is inversely proportional to R square. When I remove the sign of proportionality, it becomes M1 M2 by R square. Please remember M1 and M2 are not masses. M1 and M2 are
Pole strength.
pole strengths of the magnet, है ना? थोड़ा याद रखना है यहाँ पे. So when I remove the sign of proportionality, I introduce a constant, right? That constant is K M1 M2 R square, and even this constant is very known to you. This constant is equals to mu naught by 4 pi, which is basically what, 10 to the power minus 7 units, right? Whatever units will be there, you'll write it on your own. So F is nothing but mu naught by 4 pi M1 M2 by. This is the magnitude of magnetic force between the two poles of strength M1 and M2 separated by distance R. Can you see it is very similar to something?
Yes, sir. The Coulomb's law of electrostatics.
Exactly. In electrostatics, see how I'll rearrange the whole thing, na? And acha, by the way, whatever I am doing is basically what? Magnetostatics. Okay. Same thing word also. So the electric force was basically 1 by 4 pi 1 by epsilon naught Q1 Q2 by R square, and here the magnetic force will be mu naught or it is mu naught by 4 pi, no? So I can write it 1 by 4 pi mu naught m1 m2 by r square. So can you see over here? This 1 by epsilon naught is exactly analogous as mu naught. 1 by 4 pi was there only. Q1, Q2 analogous to m1, m2, and r square was there only. So can you see over here how things are analogous? Do you remember Gauss law? What was Gauss law? Right hand side of the equation, do you remember? Q enclosed
Q enclosed by epsilon.
by epsilon naught. I can write it like this. And Ampere's circuit law, if you remember, right hand side, it was the current enclosed
Mu naught I.
multiplied by mu naught. So can you see? Can you see the
Yes, sir.
similarities going on? Anna? So all these things are very, very similar. How electric field behaved in the case of E dot ds. Here the magnetic field behaves V dot ds. Some properties are different. That is why here it is surface integral and here it is loop, over a loop, closed loop, right? This is the Gauss's law for electrostatics, and this is basically the Ampere's circuit law. Because the Gauss's law for magnetism, B dot ds is equals to 0. Yes or no? I taught you about that also. B dot ds is
Yes,
0.
sir.
Why it was 0? Because the line which was penetrating through the loop was coming back and penetrating into the loop again.
Mm.
It was in the form of closed circles, no? So that's why the overall current, overall magnetic field lines which were passing through that area was 0. So that's why. Anyways, so I think you find the similarity of magnetostatics with electrostatics, right? Where what is mu naught?
Yes, sir.
Mu naught is called as, what is mu naught?
Permeability of free space.
Very good. The absolute permeability of free space. Acha, what if these poles were placed in a medium? If they were in a medium, then what will happen? That force will be equals to mu naught will be replaced by mu by 4 pi. Do you remember epsilon naught was replaced by epsilon? Similarly, mu
Yes,
naught
sir.
will be replaced by mu. Where what is mu? This is basically the absolute permeability of the medium. And please remember, this mu is nothing but mu naught multiplied by mu r. You remember epsilon was equals to epsilon naught into epsilon naught r, or basically k, right? So the same way we define mu r over here. Where mu r is basically called as the relative permeability of medium it just behaves like a dielectric constant. For soft iron core, this is maximum. Mu r is equals to 1. So the permeability is mu naught. For soft iron core, I'll give you a number. Let me just search on internet. I'll give you a number for that. I think it's infinite, but they might have given a very big number. So for soft iron core, where's my phone? Relative permeability of soft iron core. some ferrite and permalloy materials can have a permeability of 10,000 or more. So ऐसे तो they haven't given any number as such. Acha, I'll share you one link, है ना, guys. How do you share the link? Share it to WhatsApp Business and 12 group. I have shared one link in the group. Why is iron the best core for an electromagnet? Read this whole article once. Okay, you'll understand something more about this relative permeability, and I couldn't find any number to it, but we can assume it is very high. Okay.
Okay, sir.
So generally the permeability will be very high. So anyways, is this clear, guys? Is this clear?
Yes, sir.
Now similar to electric field, we can the whole chapter can be revised again. How can you how did you define electric field? The same way we can define magnetic field as well. The magnetic field intensity or the magnetic induction in reference to magnetic poles. So we know this particular thing, just like whenever we had a charge, this charge applied a force on another charge which was placed in the vicinity. Do you remember this electric field? It experienced one more force, right? This region was basically termed as what? The electric field. How did you define electric field? How did you define electric field? It is the space or region surrounding a charge where the force due to it can be felt, right?
Yeah.
So similarly, if I have an isolated monopole, which is hypothetical, obviously, right? So
Yeah.
suppose if I have a monopole, let's say this monopole is north, okay? So this monopole will also create certain, will have a space around which if I placed another monopole, M naught, then this monopole will experience a force. So can you see over here, a magnetic pole, it produces a magnetic field in its surrounding, and in this region if any other pole is placed, then that pole will experience certain force, right? Are yes or no?
Yes, sir.
So similar way where I defined, you remember for defining this electric field intensity at this particular point, I made this as my source charge, I made this as my test charge, and you know the properties of source charge and test charge, right? So similarly, this will be my source monopole and this will be my test monopole. So just the way where I defined electric field at a point, let's say P, is basically the limit Q naught tending to 0 Fe divided by Q naught. Do you remember this? Okay, you know that Q naught
Yes,
is
sir.
very small so that it doesn't affect the electric field intensity due to plus Q.
The source charge.
So that's why for those neat people, this is just a mathematical way of representing that Q naught is very small. Can you see Q naught tending to 0? That implies the value of Q naught is so small that it doesn't produce enough magnetic or enough electric field to distort the electric field of this source charge. Are you getting my point? Similarly, the magnetic field at the point P will be defined as limit of this m naught tending to 0. Where to where? Oh, sorry, I made the brackets on the different thing. My bad. Okay, and this will be the magnetic force divided by m. Or simply, if you don't want to use this, and here the magnetic field at point P is basically magnetic force divided by m. You can simply write this. Okay, please remember there Q was source charge and here M is the source monopole. Q naught was the test charge, assumed to be very small so as it doesn't affect electric field in space due to source charge. Similarly, M naught will be a test monopole and this test monopole is assumed to be very small so as it doesn't affect the magnetic field in space due to the source. Are you getting my point, guys? Can you see it's very analogous? Even sometimes
Yeah.
I don't teach this chapter also, no. Even if I don't teach you this about monopoles and all, no, still you can apply the same logic of electrostatics in this case. Okay. Please remember, this whole concept of this monopole is theoretical. Please remember this particular thing. This concept is just theoretical, as monopole doesn't
Exist. But then,
Doesn't
sir,
exist.
how does this hold true if monopoles themselves don't exist?
There is
Because
बेटा एक मेरे ख्याल से फिजिक्स में एक ब्रांच होती है जिसको कहते हैं थियोरेटिकल फिजिक्स, है ना. वो लोग सिर्फ थ्योरी बना के चले जाते हैं और उनको मतलब देयर इज नथिंग टू जस्टिफाई दैट थ्योरी. टिल द टाइम फिजिक्स में you give a theory, some experiments being conducted on this thing, if some experiment after conducting some experiments कुछ अप्लाई भी करने में हो जाए तब जाके वो चीज तुम्हारी किताब में मिलेगी. And if it is just theory, then how?
got it.
Okay. So anyways, please remember this concept is just theoretical. So इतना लोड लेने वाली बात नहीं. Okay. So anyways, I'll just shift it a little bit on the left side. Chal. You can write the note. This is a theoretical concept. Actually, may not true. Because actually, may it doesn't exist. What happened? क्या हुआ भाई? कॉल पे क्या? I already told you know okay how the positive charges behave in electric field the same way north pole will behave in magnetic field, and how the negative charges behave in electric field same way the more this will be. So if suppose I have a uniform electric field like this. Yes. Why am I teaching with this analogy? So that you know you will be able to correlate between chapters. That's the sole reason why am I doing this. Okay. So suppose if I have a plus q1 charge, then what will be the force on this charge? It will be q1 into E vector. Can you see the direction is same as electric field? Why? Because the charge is positive. And suppose if I have another charge which is minus q2, so it will be experiencing a force q2 times E, but in the opposite direction. Yes. Similarly, if I have a uniform magnetic field, and let's say if I have a pole and this pole is north, so M1 pole strength and north pole, then where exactly will it experience a force? In what direction will it experience a force? Hello.
In the direction of magnetic field.
In the direction of magnetic field. And what will be the magnitude of this force? M1 times of B. Just like Q1 times of E, M1 times of B. Similarly, if there is M2 and it is south pole, then it will experience a force in the opposite direction. Not minus, don't write this. Why are we not writing the minus sign? Because direction we will think and magnitude will write. So I think it is pretty much clear to you. Now you got clarity on the why did I say the positive charge behaves exactly like a north pole. And are you getting my point now?
Yes, sir.
So now we'll see the magnitude of the magnetic induction due to a magnetic pole. The next heading. Okay. Guys, can you see there is a magnetic monopole M which is placed at O, and this monopole is north, and this is creating a magnetic field in space. At this particular point P, I want to find out what is the magnetic field intensity, or basically the magnetic induction at this particular point. So what will I do? I'll place a test monopole over here. Yes or no? When I'll place a test monopole, what will happen? This test monopole, since it is so both are north, so hence it will be experiencing a force, magnetic force. What will be the value of that magnetic force? Will it be mu naught by 4 pi into m naught denoted by x square divided by x square? Yes or no?
Yeah.
So what will be the magnetic field intensity or the magnetic induction at point P? What will be the magnitude of this thing? The value of magnetic field will be basically this magnetic force divided by m naught. So this will be equals to mu naught by 4 pi. M naught and m naught will get cancelled, only m by x square. So again, the formula is also similar. Most of the things will be similar. We'll see some more cases. Whatever we can finish in today's class, we'll finish. In the next class, we'll see some more, and then we'll start with the Earth's magnetic field. Vectorically, I can write mu naught by 4 pi into m by x square into x cap. Remember? If I say x cap is basically a vector from here to here. Although, have you ever seen me using this vector form of Coulomb's law? Ever? Have you ever seen
No.
me using this? No, na. I will never use it. It's just writing for school purposes. Although even I don't know whether your teacher has taught all this. Has a teacher taught this? Because I think general teachers say it is similar to electrostatics and they skip it. Guys, have you seen this thing in school?
So we
Yes,
didn't do
sir.
this
Bit.
expression and all.
So you didn't do any equation and all. Chalo, koi
No,
baat
Our
nahi.
teacher taught this.
we did dipole moment.
We are doing dipole moment. That is the next topic. Once you are done with this, then write down the heading: magnetic dipole moment of a bar magnet. नहीं चल रहा करते उससे नहीं लिखाएगा सिर्फ से लिखाएगा ट्राई कर ले अच्छा guys, do you know this particular this pen tablet which we have now, that this also works on the principle of magnetic induction and all? Have you seen when you try it with the help of your fingers, it will never happen? अच्छा, you people know about pen tablets, right? सबने देखे हैं?
Yes, sir.
So whenever you write with the help of your finger, it won't write. It will write only when you write with this pen, and that too. And can you see when the pen is at a certain distance away from the pen tablet, then only this pointer moves.
Yes, sir.
है ना? When you keep the distance more, it will never happen. Why does this thing happen? Have you seen? I don't have any contact. Still, it is recording this thing. It's because of the magnetic substance inside this particular thing. This whole thing works on magnetism.
Okay.
Anyways, is this clear, guys? Did you write the heading?
Yes, sir.
Okay. In the next class, we'll see some more things and all, but I'll just give you this magnetic dipole tell you about magnetic dipole in today's class. Just like an electric dipole, there is this minus q charge, there is this plus q charge, which are separated by a distance 2d. Then you define a dipole moment vector. Do you remember these two charges were fixed with respect to each other? So it defined a dipole moment. Right or wrong, guys? If this distance was d, oh sorry, not distance is 2d, right? So you basically defined one vector. Why am I right? Basically you defined one vector which was pointing from the negative charge towards the positive charge, and you denoted that as p vector. Remember, p vector was called as the electric dipole moment, right?
Yes,
याद
sir.
है किसी को? And do you remember, it was basically what? It was the magnitude of charge multiplied by the
distance between.
So was it like this 2qd vector? Do you remember all this? ये सब याद है? पहले अपन ने किया है. We already studied all this.
Yes, sir.
In the similar way to electrostatics, if I have a bar magnet with its south pole over here and north pole over here, can you see south pole is behaving exactly as this negative charge, north pole exactly as this positive charge? Let's say the pole strength is m. Acha, for simplicity purposes, from now onwards, whenever I'll write plus m, you understand it's north pole, and minus m to understand it is south pole, okay? Please remember, plus m minus m does not exist. Conceptually it is wrong. Okay, Kangya. Where did I teach you pole strength? This pole strength, it is always positive. It cannot be negative. Okay, but still only for the simplicity purposes I am doing this, है ना? Whenever I say plus sign, automatically your mind should go that it has a pole strength of m and it's a north pole. And if I say minus m, then it's a pole strength of m and south pole. Okay,
Okay, sir.
so note this thing, है ना? This thing which I am writing is conceptually wrong, but for the sake of simplicity I am writing. If you want, I can remove it. You will not be confused in this, है ना? Now let us assume the distance between the two is how much? 2D. Then there will be one more vector which is denoted by capital M vector. This capital M vector is basically called as magnetic dipole moment of this bar magnet. So similarly, capital M vector is equals to M into 2. Can you see the difference? This is capital M is magnetic moment and this small m is pole strength. Always remember this magnetic moment is a vector quantity. And what is the direction of this vector quantity? The
South to
direction is
north.
always from south to. Just like this had from direction negative charge to positive charge, this has the direction of magnetic moment will be from south pole to north pole of the magnet, and the SI units will be ampere into meter square. Why ampere into meter square? Can you see M itself was ampere meter multiplied by one more meter, ampere meter square. Clear?
Yes, sir.
Okay, guys. After this, we'll study in the next class. We'll see, what is the direction, what is the magnetic field due to a bar magnet on its axis, on its equatorial axis. Do you remember all this? Yes, sab yaad rakhna. We'll be doing questions as well, and we'll be having some more revision points, and then we'll do the questions. Okay. So next class, a little bit of numerical part is going to come. Only we completed only 3 pages today. Chale, no problem. Thank you, guys. We'll see you again in the next class.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Bye.
Thank you, sir.
Hello, Cyril. You connected early?